All right, let's cover Unit 5, which is water and solutions. This is a very big unit, probably the most complicated in my opinion, so the video will be uh, longer than usual. Let's start with question 1. What is the percent water in magnesium sulfate pentahydrate MgSO4 5H2O if the molar mass of MgSO4 is 120.37 and water's molar mass is 18.02? So the formula for percent water is going to be part over whole times 100, which means the um, part will be mass of water, mass H2O, water, in 1 mole of compound over mass of the 1 mole of the whole compound times 100. This is not given on your test, so you have to memorize this. Um, it's not that hard to memorize once we get through one practice problem because you will actually know what each of these actually mean. So let's start. We have to figure out the molar mass of the total compound MgSO4 5H2O first. We're given MgSO4, so all we got to do is find the molar mass of 5H2O. 5H2O means that you're multiplying 5 with 2. You're multiplying 5 with the invisible 1 that's linked with the oxygen. 5 times 2 is 10, so we have 10 hydrogens. We have 5 times 1, the invisible 1, which means that we have 5 oxygens. All right, with this information, we can now calculate, since the molar mass of hydrogen is 1.01, we add that, or multiply that by 10 and add it to 5, since there's 5 oxygens. 5 times molar mass of oxygen is 16. When you add all this up, you are going to get 90.1 grams per mole for 5H2O. With this information, we have just calculated our part. All we got to do is calculate the whole now. For the whole, we're calculating the whole thing, MgSO4 and 5H2O. We are given MgSO4 here. We've calculated 5H2O here, so all we got to do is add those together. We have the MgSO4, 120.37, plus we have the 5H2O, which is 90.1, and the whole will be 210.48 grams per mole, and this is the whole. Therefore, all we got to do now is take part over whole and multiply it by 100. So that 90.1 over 210.48 times 100 will give you 42.8% H2O water. That is your final answer. Alright, let's try number 2. What is the molarity of a solution containing 5.32 grams of sodium hydroxide, NaOH, and it gives us the molar mass, in 100 milliliters of solution? This is also not given on your test, but molarity, capital M, its formula equals moles of solute over liters of solution. This is not given on your test. You have to memorize this. Let's draw that asterisk a little better. Not given. All right, so let's take a look. In order to find our molarity, we need to find the moles of solute and the liters of solution. We're given milliliters, and we know that 100 milliliters equals 0.1 liter. So we have liters all covered. We just need to use dimensional analysis to convert grams of sodium hydroxide into moles of sodium hydroxide. Start with our given data, grams of sodium hydroxide. For every 1 mole of sodium hydroxide, we're going to have 40 grams of sodium hydroxide. And our grams of sodium hydroxide cancel out, giving us moles of sodium hydroxide when we know, and that tells us we are good to solve. We're going to do 5.32 times 1 and then divide it by 40, which is going to give you around 0.133 moles of sodium hydroxide, and that covers our moles of solute. Therefore, now we're going to get this equation and put our moles of solute we just found on top, divide it by the liters, 0.1, and that is going to give us our final answer of 1.33 molar, capital M. And that is our final answer. All right, let's try number 3. How many milliliters of a 7 molar sodium chloride solution is required to prepare 500 milliliters of a 0.45 molar solution? Taking a look, we're going from 7 molar, which is very high in concentration, to 0.45 molar, which is very low in concentration. That means we are diluting the solution, which means we are going to use the dilution equation. Use dilution equation. This equation is not given, so you have to memorize it, but it's very simple. M1V1 equals M2V2. Not given. All right, so let's take a look. The M stands for molar, which is the molarity. V stands for volume. All right, so we're looking for how many milliliters, and we're given we look at our 2 molars and we choose the highest one as M1, the lowest one M2, and we're using this 500 milliliters as our volume 2 because the volume is linked with the second molar. So all we gotta do is grab our equation and plug it in. So make sure that your starting units ml and the starting unit or ending units ml match, and that molars of course matches. When we have this scenario, we do not have to convert to liters as we're going to give an answer of milliliters as well. Let's see. M1, we are looking for the volume 1. So we have M1 here. 7 molar times volume 1 is going to be equal to the molar of number 2, 500 milliliters, times our second, we're going to put our, doesn't really matter, but let's follow the format. We have our 0.45 molar solution and 500 milliliters of our volume. Grab that. We are going to have, if we see volume 1 as x, we are going to have 7x equals 225 on this side. Divide by 7 on both sides, and you get V1, which is x, equals 32.14 milliliters, and then we put NaCl. That is our final answer. Let's take a look at number 4. All right, just scroll up a little. How many grams of CaOH2, and it gives us the molar mass, are needed to make 20 milliliters of a 0.1 molar solution? So in order to find this one, it's a little complicated, but we look at our unit, right? And this is molarity, capital M, molarity. This equals moles of solute over liters of solution. Remember that this equation is not given as talked about in the previous question. So all we got to do is now set this up to find our moles, because in the end, we're looking for grams. That means we have to convert, meaning we have to use the definition, the units of molarity, in order to find our moles of solute. We're given 20 milliliters, which is equal to 0.02 liters. All you got to do is divide it by 1,000. And so we take this 0.2 liters, and we have the liters. We have our molarity, 0.1, so we can set it up as 0.1 molar equals the moles of solute over 0.02 liters. And solving for the mole of solute, we take 0.02, multiply it to 0.1, and you are going to get your mole equals 0.002 moles of CaOH2. All right, keep this number in mind. We are going to grab this and convert it into grams. All we did here was use our molarity definition to find the amount of moles in order to get that to convert to grams, the final answer it needs. Take 0.002 moles of CaOH2. For every 1 mole of CaOH2, we have our molar mass, 74.10 grams of CaOH2. And we know that moles of this and moles of this cancel, leaving us with grams in the end. We are good to solve. Everything is 1 on the bottom side, so all we got to do is multiply this number by this number. In the end, it will give us 0.1482, which I'll just round to 0.15 grams of CaOH2. That is our final answer. All right, let's move on to question 5. How many grams of sodium fluoride, NaF, are needed to prepare a 0.4 molal, that is molality, lowercase m, sodium fluoride, NaF, and gives us a molar mass solution that contains 750 grams of water? So let's define molality first. Molality is going to be moles of solute over kilograms of solvent. All right, with this information, we have to figure out the moles based on our kilograms, which we can convert from our grams, and our given molality data, much like question 4. So we have 750 grams, which we know, which is 0.75 kilograms. And then we're going to set this up using our molality equation. So let's set it up over here. We're going to have 0.4 molal being the molality, equals the moles of solute over the kilogram we just found, 0.75 kilograms of solvent. Let's just write kg. Okay, multiply 0.75 to 0.4 to get moles of solute on its own, and you are going to get 0.3 moles of NaF, sodium fluoride. Take this number, we are going to set it as dimensional analysis, 0.3 moles of NaF, and try to find the grams. Every 1 mole of sodium fluoride, we're going to use the molar mass. We have 41.99 grams of sodium fluoride. Moles of sodium fluoride cancel on both sides, and we have grams of sodium fluoride left, and we have only ones on the bottom, so we just got to multiply this and this together, which is going to give us 12.597, which I'm going to round to 12.6 grams of sodium fluoride. And that is our final answer. All right, let's take a look at number 6. What is the freezing point depression, FPD, of an aqueous solution with 10 grams of glucose, C6H12O6, and 50 grams of water? And it gives us this KF. All right. So in order to solve this, there's a lot of things that are happening. So freezing point depression means that it's asking for temperature. Asks for temperature. All right. And so we take a look at everything in our question here. We know that C6H12O6 glucose is going to be a covalent compound. We're going to keep that in mind for later. And we have grams. Okay, so what equation do we have to use? Well, we have we have, let's see, we're solving for temperature, T. We have our K, KF, we have K. We have we can find the molality, and we can find the I. So we have to use this equation, delta T equals KMI. This equation is actually given. You do not need to memorize it. Just I would remember what these stand for, which I'll explain right now. So this is the change in temperature. Change in temperature. This is our K value, which is it's just a constant K. Constant K. We have molality right there, and this I is the special part. This is called the Hoff, um, the Van 't Hoff factor. Van 't Hoff. All right, so with this information, we're going to try to solve for delta t. Given the fact that we have k, we can find m, and we can find I. So make things easier, let's figure out what our k is first. K is given. This is 1.86. Okay, that's good. Next, let's solve for m. M, molality. And molality is equal to the moles of solute over kilogram of solvent. And remember, this molality and molarity is not given, so you have to memorize it. All right, so moles of solute we know because we can calculate it. Okay, so when we try to calculate the moles, we have to use dimensional analysis. We're given the fact that we have 10 grams of glucose, so let's do this over here. 10 grams of glucose, C6H12O6. We use this, convert it using grams. For every 1 mole of C6H12O6, we have, let's take a look at our molar mass, 180.6 grams of C. Let's write that up better. C6H12O6. Running out of space here, but we know that grams cancel and we're left with moles of C6H12O6 on top. 10 divided by 180.16 will give you 0.0555 moles of C6H12O6. All right, with this information, we have the moles of solute. The kilogram of solvent is going to be not this 10 grams, but this 10 grams of water, because we know that glucose is the solute, therefore the water is the solvent. So we take 50 grams, and we know that 50 grams is equal to 0.05 kilograms. With this information, we just figured out our kg solvent, and we can solve for molality. Take our value for mole, 0.0555 on top. We take our value for kilograms, 0.05 on the bottom. Divide these, and you're going to get 1.11 molal. Molal for lowercase m. We're going to keep this number in your head, and we're going to use it in our KMI. Let's calculate I, though. I, we said, was the Van 't Hoff factor. The Van 't Hoff factor basically means the number of particles we have in our solute. C6H12O6, C6H12O6 is a covalent compound because it does not have a metal in front. So covalent, if you remember, is a nonmetal plus a nonmetal, while a metal is going to be, ionic is going to be a metal plus nonmetal. You know that C6H12O6 is covalent, and the Van 't Hoff factor for covalent is always going to be 1, and that is because the covalent substance is a non-electrolyte. Therefore, Van 't Hoff factor I equals 1 for covalence, and we now have I, we now have our molality, and we know our K. Therefore, we can go ahead and try to solve delta t. All right. Let's do it in a different color just because we have a lot of stuff going on. Delta t equals kmi. We have k value of 1.86. We have our m value, molality 1.11. We have our I value of 1. Multiply all those three numbers we just found, and you are going to get 2.0646, which I'm going to round to 2.1, and this would be our degrees Celsius. But we're not done yet because this is an incomplete answer. Let's write this on top, which is 2.1 degrees Celsius. Because we are looking for the freezing point depression and our solvent is water, the freezing point depression means that when you're adding to the solution this glucose, the freezing point depresses or decreases. Therefore, the freezing point of our solvent goes down because of the presence of glucose. Because of that, we have to take our water, the solvent's freezing temperature, and we have to basically subtract it because this is the freezing point. The lower the temperature means we have to subtract, and we are actually making the freezing point go lower, hence the depression. The freezing point of water, if you don't know already, is 0 degrees Celsius. Our calculated freezing point depression of where the freezing point depression of our solution, or sorry, solute, making the solvent go decrease, is 2.1 degrees Celsius. Basically, in simple terms, that means when you calculated this, it means that adding your glucose in 10 grams of glucose in 50 grams of water will make it go down, will make the freezing point go down 2.1 degrees. Minus 2.1 degrees Celsius, you will get negative 2.1 degrees Celsius as our final answer, the freezing point depression. All right, you will see some of this same logic in our seventh question as we look for the boiling point of a solution. Take a look. What is the boiling point of a solution that contains 1.25 mole CaCl2 in 1400 grams of water? And it gives us the K for our equation. We know that we're using the same equation as before, delta T equals KMI, and this is given, so do not worry about that. I'll even make a note on the side and actually change that to a different color again. Delta T equals KMI, and this is given. Let's just make it a little better. All right, wonderful. So as again, we're solving for the delta T. We're given K. Let's find the I. Or let's go with M first. The M, molality, equals the moles of solute over our kilograms of solvent. All right, and so we have our moles of solute, and we have 1400 grams, we know, is 1.4 kilograms. And surprisingly enough, they give us all of the numbers we need. That makes our life easier. 1.25 moles of solute over 1.4 kilograms of solvent we just found. Divide those, and you will get 0.8928 mole. For this question, I'm going to save the rounding for later, so the answer is more accurate. And let's calculate the I value. Find the I value. So this time we have a covalent because we have a metal and a non-metal. So we have a metal, non-metal there. Okay, wonderful. And we have to look at, since this is not a covalent, our Van 't Hoff becomes a little more complicated. So we have to ask ourselves, how many ions are made when CaCl2 dissociates? And that basically means that we're going to break this into its respective particles. So if we take CaCl2, it can break down into 1 mole of calcium, and since we have that 2, we can break that into 2 moles of chloride, so chlorine. So we have 1 mole here, we have 2 moles of Cl there. We have 1 mole plus 2 moles. So in this case, each mole is going to be a particle. Therefore, 1 plus 2 is 3. So the I value equals 3. With this information, we have molality, we have I, and we have K given. We can go ahead and solve for delta T. Go ahead and do this in another color. We have delta T equals KMI. K value is 0.512, as given here. M, molality, we found 0.8928, and our I value, which we found, was 3. Multiply all those out, and it is 1.5, and then we are solving for temperature, degrees Celsius. But we're not done yet. The same concept of the freezing point depression applies to the boiling point. Although it doesn't mention it here, this actually should say boiling point elevation. This is because when you're adding a substance to a solvent, we have moles of solute. The solute is the CaCl2. Solvent is going to be our water. We're actually increasing the temperature that it'll boil because we're adding more stuff in it, right? That's logically correct. The more stuff you have in the solution, the more time it's going to take and more temperature it's going to take to actually boil it. Same thing applies for freezing. So we can't just leave it as 1.5 degrees Celsius. We have to add it on to the boiling point of water because it's boiling point elevation. We're increasing the boiling point of water by this much. So the boiling point of water, if you haven't known already, is 100 degrees Celsius. Adding 1.5, the number we calculated, degrees Celsius, will give us in the end 101.5 degrees Celsius as our final answer, delta T. And that is it.